Welcome to the first ever AIAA BWSI Build a CubeSat Challenge final event. My name is Rebecca Keenan. I'm the lead instructor for the Build a CubeSat course. Over the past several months, teams of high school students from across the country have been working through this rigorous online course to learn how to design, build, and test their very own satellite prototype. After completing modules on orbital dynamics, the space environment, systems engineering, and satellite development tools, including Python programming, the students accepted the challenge to complete a series of hands-on projects culminating in their final presentations today. Each team began developing their hardware skills by building a flat sat and taking a picture of their team with their Raspberry Pi camera. They used that flat sat to learn about the parts of a satellite through subsystem labs. During their final project, the students applied everything they learned to design their very own prototype CubeSat. Each team submitted a design review video to get feedback from our judges. They have now implemented their design and submitted a video demonstrating their CubeSat's performance, which we'll see some highlights of later today. This program is run as a collaboration between AIAA and MIT's Beaverworks Summer Institute. It's made possible by the contributions of experts from MIT campus, MIT Lincoln Laboratory, and Woods Hole Oceanographic Institution, as well as all of the mentors and coaches who directly supported students. Here to tell you more about Beaverworks is Joel Grimm.
Hello, my name is Joel Grimm. I'm here at MIT Beaverworks, which is a collaboration between MIT and Lincoln Laboratory. I'll come back to collaboration in a minute, but I'd like to tell you why Beaverworks is important. What is Beaverworks? Beaverworks is an idea, and MIT is a place where ideas are fostered, grown, and sometimes even kicked around a little bit to see if they're any good or not. The idea at Beaverworks, started by our Beaverworks director, Bob Shin, is a place where more ideas can be grown. So Beaverworks is a place created by Lincoln Laboratory and MIT out of collaboration for collaboration. As a place, and actually we're located in more than one spot, we're on MIT and have our original space at 300 Technology Square, and now have newer space in Building 31 with the Aero Astro Department. But that's the thing about ideas, they tend to spread. These places serve many purposes by design, for collaboration, for classrooms, and prototyping. The idea that we can take real-world projects that we see at Lincoln Laboratory and challenge MIT students to develop new and unique solutions, researching, testing, prototyping, as they learn how to be scientists and engineers is one of the strengths of Beaverworks. An idea is just an idea until you build it. And the shops are where you can do that, to go from ideas to prototypes. So much is learned in the process of creating and building. And as collaboration is key to innovation, we want the collaboration with scientists and students to inspire great things for them to do more and go farther with their ideas. Beaverworks inspires students to do great things and lead to more great things, like the Beaverworks Summer Institute. It's a place like MIT where ideas are encouraged and brought to life. It was started in 2016 in response to a challenge to Dr. Bob Shin to create a program that uses the MIT mindset to collaborate, to work together, to use projects to learn how to do things, and with a focus on computer science and artificial intelligence technologies, and specifically for high school students, because we saw students coming into college without some of those skills. This is what BWSI is at the core. It's project-based with teamwork, and we have scientists and engineers who are doing active research coming to teach courses in the summer. It's so exciting to see them be able to share their research with students. Our first year started small with 46 students, but we had big plans to move forward on this. We started with the Autonomous Race Car Challenge, which was a college level course for MIT students. Bringing it to high school students and seeing them succeed was amazing to see them learn to program by creating these autonomous cars. Flashing forward to our 6th year in 2021, we were able to pivot to run a virtual program, but we're still growing, still creating new content, and still impacting more students. We're creating satellite programs in other areas. They're able to use our same content. We're adding new content every year and increasing the number of skills that students can learn about in different technology areas. Expanding the impact of BWSI. We've got many ways we're trying to do that. We're creating more courses every year, like I said, but not only are we creating more content for the summer program, but we're also putting that content online to make it available for independent study. In the spring and the fall, we have shorter programs that focus on getting underrepresented groups and younger students involved. And finally, we're developing partner programs like the Build a CubeSat program, partnering with professional organizations that help provide the guidance and the mentoring for student teams to build their own prototypes and learn engineering in the process. Finally, BeaverWorks is transformational, providing opportunities for students to learn, to grow farther than they thought they could, and become more than they are. Thank you.
Thank you, Joel. Like Joel mentioned, the Build a CubeSat Challenge is a partner program. We have partnered with the AIAA New England chapter to help organize and judge the challenge, as well as recruit mentors to work directly with each team and provide regular office hours. Here to tell you more about AIAA is Hiro Endo.
Hello, everyone. Congratulations for making this far. My name is Dr. Hiro Endo. I'm from a company called Test Devices, Schenck, USA. I test jet engines and rocket motors, propulsion parts for my profession. But today, I'm here to represent the American Institute of Aeronautics and Astronautics to congratulate you for going through the BWSI Summer Institute Challenges and introduce you a little bit about our institute and what we can do for you to support your journey. So you made it. I hope the challenge was worthwhile and you enjoyed the journey so far. It's not easy to learn new things and also work as a team, but it's an essential part of being an aerospace engineer. One person can do so much, but as a team, you can achieve so much more. So starting your real journey now from here, you're the next generation of aerospace engineers and rocket scientists. Are you ready to take on the bigger challenges? Let me introduce you to what American Institute of Aeronautics and Astronautics can help you with, or AIAA. So we are a community of aerospace professionals. We're worldwide largest aerospace technical society, founded back in 1963, and today having 30,000 members worldwide. People are passionate about aerospace and science and willing to help young people like yourself to join the cause. Our mission is to address the professional needs and interests of aerospace workforce, and we're here to support you and help you become aerospace engineers and rocket scientists. So for you, as a young student, joining AIAA is free. So this is a great opportunity. And when you join us and become a part of our community, there's a lot of things you can benefit from. For example, you can get a guidance from experienced professionals through a mentorship match programs. You can learn more about aerospace topics on webinars and on-demand contents. You get a daily news on aerospace to keep you informed. And you get the network with a group of aerospace engineers and scientists and students through a digital platform called Engage. And then you can also enter the other challenges like this CubeSat challenges to polish and refine your skills and hone your intuition as an aerospace engineer. We also offer scholarships and grants for students and STEM educators. So join us and be a part of this great community. And if you need more information, here's the link. Or you can email us at the AIAA-BWSI@mit.edu, the email that you know very well, that you may come across through these challenges. And Good luck with your final demonstration, and congratulations to making it this far.
Thank you, Hiro. This year, the AIAA BWSI Challenge was also kindly sponsored by Lockheed Martin. This sponsorship enables us to run this program completely free of cost to all students. Here to tell you more about Lockheed is David Aronson.
I hope everyone enjoyed the Build a CubeSat challenge. Lockheed Martin has been involved with the Beaver Summer Institute and is pleased to help to support this challenge and reach out to many talented high school students. This is very exciting to me as a space employee. I've been doing this for 35 plus years, and encouraging a little about the space career and learning about a CubeSat is just wonderful. MIT and Lockheed Martin actually have a lot in common when it relates to space. If you go back in time, the first computer game was actually invented right there at MIT back in 1962, called, of course, Space War, which was great. And for those of us who played early games, that was really fascinating and was one of the reasons I went into the space business. And also another interesting note, as I've done a little work on Artemis 1 and the Orion spacecraft coming up, is, voice recognition was invented there at MIT back around 1970. And we're actually putting, the voice assistant Alexis on Orion, and which we find really cute. And when we actually launch coming up here, you could call up and say, Alexis, I want a moon rock, which I find really cute and very fascinating going forward. But there's a lot of meaningful work at our company here at Lockheed Martin. We protect lives. We are across our space tech to many fun projects, including Lunar IR, which is going to map the moon coming up, or, some of our government things. And you have a lot of interesting work that you can do here at Lockheed Martin. Lockheed Martin has about 50,000 engineers and scientists across many, many disciplines. About 12,000 of them work in our space division. This experience that you're having right now is very valuable in your upcoming college experience, and hopefully will increase your interest in space and hopefully Lockheed Martin. We have programs in all aspects of space, from commercial, civil, like the GOES weather satellite, DoD, strategic and military, including like the strategic missile defense, GPS, which we all use, human exploration like the Orion, and many, many, many more projects that we have. Lockheed Martin hires close to 5,000 engineers every year. About 2,000 of them are new hires coming to our space division. We are a firm believer in our internship program, and it's never too early to apply. Lockheed Martin hires interns even after their freshman and sophomore years in college. And hopefully many of those student interns stay for multiple summers before they graduate college. The requisition and job postings are posted early in the fall, so please get on our website early and keep an eye out open in September and October, and please start applying for an internship with Lockheed Martin. And again, I hope everybody had a very positive experience in this CubeSat challenge, and thank you very much for participating.
Thanks to the support from Lockheed Martin and AIAA, we were able to give each team and each mentor a hardware kit that included everything they needed to complete the labs and build their own 1U CubeSat prototype. Although the kits do not include space qualified components, they do include representations of each of the major subsystems that you would see in a real flight spacecraft. Here to give you some background on CubeSats is MIT professor Kerri Cahoy.
Hi, I'm Kerri Cahoy. I am an associate professor here at MIT in aeronautics and astronautics. I also direct the Space, Telecommunications, Astronomy and Radiation, or STAR Lab. One of the things we do for research in STAR Lab is we develop new technologies and we fly them to space on CubeSats. I'm very excited to be here and be involved with the BeaverWorks Build a CubeSat program because we need all the help we can get. Developing and building and operating a space mission takes a lot of people in all different disciplines, and I'm excited to be working with you guys and look forward to hopefully seeing you either working with us in our lab or in the industry in partner labs in the near future. I'd like to just show a few slides about CubeSats, their history, and how they get to orbit. On this first slide is an illustration of a mission that we're working on for NASA. It's called the CubeSat LaserCom Infrared Crosslink mission, or CLIC, and we're going to send up two CubeSats, CLIC B and CLIC C. There is a CLIC A as well, to do a crosslink of data using lasers from satellite to satellite on orbit. All right, so CubeSats. There used to be a big amount of interest around what would happen when the year changed from 1999 to 2000, and the CubeSats were invented in 1999. The CubeSat unit is called a U. One U is 10 centimeters, a cube with 10 centimeters on each side, and the standard mass is about 1.33 kilograms. You can, in theory, stack and combine your CubeSat units, kind of like Legos almost. We are working on that, as I'll show in the next slide. And here's a couple of images that show the scale of a person working on a traditional satellite compared to this little red box here, which is the size of a CubeSat. So that's about the size scale. So satellites, we basically shrunk them and their capabilities from being something that was nearly school bus sized to something that was much more like a shoebox. We are working at MIT in my lab on an idea to stack them together even more like Legos. So this is a project that two grad students, Mary Dahl and Esne and Meng, are working on, where we have a robot to put together CubeSats on orbit. And so we had the students develop parts that snap together and can hold an electronics board in each, and you could have a container of different parts on orbit and then be able to put them together on orbit in just the way you needed, with just the right amount of propulsion or the camera or the electronics board you might need, or to replace something. So this is just to emphasize that we really would like to stack them together like Legos, even if it's not quite like that right now. And this would reduce cost, and the satellites wouldn't need to really be tested, assembled on the ground to survive the rocket shaking, because they'd just be packaged in their boxes. And it would allow us to get things on orbit even faster than we already do. So this object looks a lot like what a jack-in-the-box looks like, but it's not. It's a satellite. So one of the ways that CubeSats, they were able to convince people to let CubeSats get to launch inexpensively, is to have them be protected. If you have a big expensive spacecraft on a rocket, you don't really want to put it in danger by having this cheap, inexpensive student-built satellite on the rocket with you. So they basically decided that, oh, we'll make a little safe box, we'll put the CubeSat in it and then bolt it to the rocket. And that way it'll only come out after the main satellite's gone, when everything's safe. And that ended up working out. So the spring-loaded box is a CubeSat deployer box. You literally load the satellite in it, snap the lid shut, and then bolt it into the rocket, kind of like this. And not joking, you literally bolt it onto the rocket. So this is an example of some of the earliest ones. On top of the Bion M1 spacecraft on a Soyuz initially. So this is BSat 2, 3, and Aussie, and one of the very first doves in the back right. So this is a pretty exciting picture, but yeah, you literally do just bolt them to the rocket, and then you have to get them to orbit. So this is after multiple years of launching CubeSats, people started to really do it in earnest. And this was one of the first missions. It's a PSLV that launched from India, where they actually figured out how to get over 100 CubeSats on board the rocket with one big satellite at the same time. And so this is a kind of fun video that shows 88 Planet CubeSats, as well as several others being deployed, kind of like clowns from a clown car.
From both sides, one after another.
And they're just coming out one after another, and you can see them kind of deploying. Off they go. And if we wait a few more seconds, they deploy the next one, then they open the box, the spring pushes the CubeSat out, and they just kept that up for a whole bunch of minutes to get all 100 of them out. So that's a big deal, and it's kind of where we are now. So that's one way, is just to be directly launched on the rocket. Another way is to have kind of an intermediate trip where you get put on the rocket, but instead of being bolted to it in the deployer, you're packed away as cargo, and you go to the International Space Station, and then the robot arm or an astronaut deploy you. Here are some examples of that. So on the left, this is a cosmonaut that is pitching out. a Peruvian CubeSat. I'm just going to advance to where the action is.
Ready to cast it away
And
for its science mission.
so he's on an extravehicular activity, an EVA, and had that CubeSat in his pack. And his job is to deploy it. And so kind of like opening day for baseball, perhaps with a little bit more of a gentle throw. That CubeSat is on its way. Another way to do it is to, once you're unpackaged from the Cygnus spacecraft, is to be deployed from the robotic arm. So they actually put the boxes, the deployer boxes, on the robotic arm, and then they command the deploy. This is actually one of our CubeSats being deployed. Videos are all courtesy of NanoRacks. So these are fun. And this is what they look like. But the nice part about being launched from the space station is that they have cameras and astronauts with the cameras. And so you can get really nice pictures of the deployment, which otherwise you're kind of stuck with the slightly grainy video from the rocket, like we were showing from the PSLV. So it's always fun when you get the nice images from the space station. And just to wrap up, we've got a couple more coming up next on the launch pad. So these were two that completely different missions that were developed in my lab that ended up being integrated into the same deployer completely by chance at NanoRacks this past March. On March 30th, our students went down there and put these together and integrated these. So this is Click-A. This is a laser communication downlink 3U CubeSat, and this is Beaver Cube 1, which will be taking pictures, thermal images and optical images of the Earth for looking at coastal change and climate change. All right, well, good luck to everyone. I hope you have a wonderful experience, and I'm excited to be part of it. Thanks so much.
Thank you, Kerri. The Build a CubeSat Challenge final project challenges the teams to design, build, and test a CubeSat prototype for a real science mission. This year, we worked with Dr. Collin Ward and Paul Fusil from Woods Hole Oceanographic Institution to look at using CubeSats with an imaging sensor to detect plastics in the ocean. Here to tell you more about the science behind this year's mission is Dr. Collin Ward.
Hello, my name is Collin Ward. I am a scientist at Woods Hole Oceanographic Institution on Cape Cod in Massachusetts. Woods Hole Oceanographic Institution, or WHOI as we call it, is the largest oceanographic research institution in the world. There's over 1,000 employees, and there's also an academic programs office that is linked up with MIT, where we have undergraduate, graduate, and postdoctoral students. We study all phases of Earth and ocean sciences, and overall our mission is to better understand how the ocean works and how it is being perturbed by human forces. My personal research focuses on the fate of organic molecules in the ocean, such as crude oil or microplastics or even naturally derived organic compounds. So for instance, in the microplastics world, I study how sunlight breaks down plastics into different gases, such as carbon dioxide, that is a greenhouse gas, as well as dissolved organic molecules that can be used by microbes as food sources. The science mission for the Build a CubeSat Challenge this year is motivated by one of the most pressing environmental issues today, plastic pollution. It's estimated that upwards of 10 million tons of plastics enter the ocean each year, but the fate and ecosystem impacts of this material are poorly understood. When this plastic debris is exposed to the elements, specifically sunlight, it can be degraded into smaller and smarter particles, often called microplastics. These microplastics generally cause more harm than the larger pieces of plastic that they're made from. However, it's extremely challenging to clean up little pieces of plastic in the ocean. So one of the short-term solutions to the ocean plastic pollution problem is to clean up the larger pieces of plastic before they become smaller pieces that can cause ecological harm. One type of plastic that the community is targeting is derelict or abandoned fishing gear, such as nets. Sometimes these nets are referred to as ghost nets because we don't know where they came from or who they belong to. These materials make up nearly half of the floating plastic debris in the oceans by mass and have a huge potential to be broken down by sunlight into microplastics over time. So for example, a net that was 1 cubic meter in size could become 1 billion cubic millimeter microplastic particles as it degrades by sunlight over time. So instead of aimlessly cruising around the ocean looking for abandoned fishing nets, our scientific mission for you all was to develop a small cube satellite that could spot floating fishing gear from space. This information could then be relayed to cleanup crews on ships to remove these fishing nets before they get broken down into microplastics and cause ecological damage. I apologize that I won't be able to attend the final presentations. I have a newborn at home that needs my attending, but I sincerely hope that the missions went well and that you learned a lot thinking about the ways to solve this important environmental problem. Feel free to reach out anytime if you have follow-up questions or would like to learn more about WHOI or Earth and Ocean Sciences in general. My email is cward@WHOI.edu. Have a great summer, folks.
Thank you, Collin. Now it's time to hear how all of you approached this mission. After each team presents, we'll have a few minutes for questions from our judges and from everyone in the audience. If you're watching on the webcast, please post any questions you have for the teams in the box on the webcast page. Now, on deck, we have Team Satickens, but first up, please welcome Team Raiders.
Hello guys, we're Team Raiders. Let's get our presentation up. It's right there. Yeah, it's this one, right? No. Below. No, it's this one. Oh. Yeah. All right. So presenting the Build a CubeSat challenge. We're Team Raiders. I'm Jaime.
I'm Maddie.
I'm Ryan. I'm Gonzalo. I'm Ali. And our coach was Oscar Gonzalez, my dad. And our mentor was Connor Galligan. If Connor's here, let's say hi. So first off, we're going to talk about our system overview, which was our solution design which was included in our design review video. But we feel as if it would be nice to show you guys, how it looked like and how we planned it out, like our overall concept. So here on the right, we see the design, which is, it starts at the subsystems being initiated with the Raspberry Pi and overall CubeSat being turned on. And then the function identify plastics runs, which is an image detection loop that we are running in real time. So our code will be detecting plastics as the processing is happening. So when an image is identified, it compares it to a library of plastics to see if it's a plastic. And once an image is matched from the image detection loop, it is stored and sent over to our ground station through Bluetooth. And then we also had a creative idea to tweet this photo on Twitter, kind of to give the information out to the public on like our environmental like status of the world and how pollution is affecting our world today. And then after that is tweeted out, it will go back to the image detection loop until stopped. All right. The next slide was the system overview, which just talks about the subsystems overall. So here we have 1, 2, 3, 4, 5, 6 subsystems. And then we have the obligations these subsystems are supposed to fulfill in our project. So here we have everything in the CubeSat that is included in each subsystem. And as you can see here, like on the left, the overall structure shall contain all of the elements needed for the final demo. And we succeeded with our hardware. You're going to see in the next slide. And not included in this system overview is a ground station. It's a ground station, which is a Windows laptop with Bluetooth and Wi-Fi enabled for SSH protocol, meaning that we can run it. We can run our CubeSat on our ground station without having to be connected to the CubeSat.
Next is our system overview software. First, we use TensorFlow libraries that are used for item detection. And in our case, we use code, which uses TensorFlow to detect plastic cups and bottles, because we researched and found that plastic cups and bottles are the highest percentage of plastic in the ocean.
And then we see the code here on the right, the first picture, which is the code we used with TensorFlow libraries to detect these bottles and cups. There was also more plastics in the libraries, but we decided to use plastics such as bottles and cups.
Next, for the code we implemented to tweet the picture on Twitter, we requested a developer account from Twitter. And once we received it, we used Tweepy libraries in Python to connect our code to Twitter and tweets out the picture that we took.
Yeah, and once the picture is tweeted out, the picture is also sent to our ground station, which we have BitFies is an application we downloaded that uses SSH client to operate CubeSat through Linux terminal and manage files. So meaning that we can manage CubeSat, as I said before, through our ground station. So we can access the photos and delete photos or run code whenever.
All right, so here is our results from testing. So we've put together a short little video to cover pretty much the basics of it.
Okay, so now we're gonna run the code on our environment.
You guys here as well?
And press enter, and we're gonna see a little box come up here detecting. So here we see bottle. Move it a little bit. See, it detects as a cup. So here we see that he's holding the Raspberry Pi to detect the plastics in real time. And there we go. Okay, so here we have our ground station. So as we can see here, we have an application called BitFies that we downloaded that connects to the Raspberry Pi and our satellite through Bluetooth and SSH. So here we see that this is the Raspberry Pi just on my computer. So we see the image that we just took was right here. And now we see the image right here on our ground station, meaning that the downlink was successful in taking the photo. Also, our ground station can also do other cool things, like it can run any Raspberry Pi command since it's connected to Bluetooth. So as you can see here, it can run the Python bottle detection Pi program that takes the photo and then later uploads it to Twitter, which is what we will talk about right now.
Once our photo is saved into the ground station, we then have a bonus where the photo is tweeted on Twitter, which for Twitter, we needed to develop a developer account where we filled out a form and requested it for this academic project. And Twitter gave us a developer account and developer codes.
We had to implement the APIs in order to have the Raspberry Pi and the Twitter come hand in hand. Which had to do with the Python code that we used Tweepy, which was a Python library that allowed us to do what we're doing right now. After the photo is taken, it saves it and it posts it on Twitter.
So yeah, we see how there you saw how we're running in real time. How do I get out of this video?
Press escape.
Okay, so now we're gonna run the code on our environment.
Press escape.
Enter, and we're gonna
All right. Yeah.
All right. So the things we struggled with was, firstly, in some pieces of the code was we struggled to combine the real-time object detection and capturing still images, but then our mentor, Connor, helped us find the correct TensorFlow functions to use. We also struggled to push images from the Raspberry Pi to a Windows computer with Python, but we then figured out that we had to download images from the ground station. Something that we weren't able to figure out was to be able to include the location of the plastic when the photo was taken. So for example, if there's a picture of a bottle, like it wasn't able to tell us like where exactly it was.
Mm-hmm.
And then also something else that we struggled with was automatic image transmission, which is like when the camera sees an image, it didn't take a picture right away. Yep.
Okay, so now we're gonna run the code on
Next slide.
So for the Skeleton Flight spacecraft, if this were to be a real satellite, what we would do is have a high resolution camera so we can zoom in from outer space and take a high quality picture. We would also use transmission via radio so we can communicate back and forth with the ground station and satellite.
Mm-hmm.
Also, a propulsion system to move the satellite in space, which is what uses the acceleration for the satellite. A GPS system to detect where the satellite is and where the plastic in the ocean is located. And we would use certified grade materials so the satellite can handle the harsh conditions that it's faced in space. And finally, once the satellite captures the images, it will send them to the ground station and it will be tweeted toward Twitter.
So obviously throughout this whole project, we've learned a lot about satellites, engineering, and coding. We've also learned a lot about project management. A big part of this is time management and ensuring we're holding ourselves accountable and dedicated to this task and making sure we're going to our meetings and using our time wisely in order to meet these deadlines. Another key thing that we learned is that mistakes are inevitable. Throughout this whole project, we made a lot of mistakes, or we encountered a bunch of unexpected errors. And we just realized that that's perfectly okay. It's just important that we're able to work our way around them and work together as a team to come up with solutions. And the final thing is, we realize there's a lot of resources out there. And then there's also, you guys provided us with a lot of resources. Let's really try to take advantage of those, attend the office hours, use our mentor Oscar and our team coach. Then also, what was that?
Our team coach Oscar and our mentor Collin.
And use those resources, and don't be scared to ask clarifying questions or ask questions in order to learn and grow when we're struggling.
Yeah, we also had a lot of fun with Piazza and asking questions on there. You guys had good responses to those. So our acknowledgements, we've learned a lot about satellites, engineering, software development, Python. Even though we struggled on Python, we still had a lot of fun learning about Python. It was something that our team didn't really know a lot about. We knew some about Java, but not a lot about Python. So it was like fun to connect both of all of our knowledges to learn. Watched a lot of YouTube videos as well to really get down, since we were doing something different with the real time instead of taking a photo and then processing the photo. We had to do a lot of research to see how we would incorporate that into our CubeSat final project. We'd like to say thanks to MIT BeaverWorks Bob and our fabulous and patient mentor Connor. Thank you to Rebecca, our coach Oscar, and the rest of the teams for participating and helping each other in Piazza during open office hours and seminars. And yeah, we have an idea also that we didn't really talk about before, but we're also trying to incorporate into our CubeSat final project, was that after tweeting, we would we'd send a radio message or a radio signal to the nearest boat next to the plastic, which would be a cool idea, but we tried to see if we could code that into our CubeSat final project, but we had some problems with that as well. And yeah, thank you so much.
Thank you.
Thank you.
Thank you, Team Raiders, and congratulations on completing the Build a CubeSat challenge. Now open it up for questions from our judges here on our main stage Zoom, as well as anybody watching the webcast. Feel free to enter your questions in the webcast discussion box. So now open it up for our judges to unmute and ask you questions.
I guess I could start, Rebecca. So great job, Team Raiders. In your video, when you were showing your data collection, it looked like you were holding the camera over the bottle. And I was just curious, when you were taking your video, did you experiment at all with moving, for example, the camera at different speeds, as opposed to just holding it over the plastic? Did you find that it made a difference if the camera was moving too fast or too slow? I mean, is that something you explored at all?
Yeah, we did. It was kind of hard because the processing is weaker with our CubeSat, so it couldn't really detect, since we're detecting in real time. It was kind of hard for it to detect when we were moving it a little faster. Yeah, because it was kind of blurry as well, because the camera isn't the best resolution.
Yeah, so it's difficult to detect the bottles on the ground as it was moving faster.
Yeah.
Okay. All right. Thank you.
I think it was more of a concept idea that we did the real time, because it's for this CubeSat project, we don't really have the materials and the best cubes satellite to run it real time, but we did our best with testing it.
You guys did a great job.
Yeah, thank you.
We do have one question from the audience. What would you expect the nearest boat to do when they received the notification?
I would say we can ask like kindly if they could go pick up the plastic, and we're not gonna like force them to pick up the plastic, obviously, because they can't control that, but yeah, just ask.
I think it's also just making them aware that the plastic is there, because sometimes just making people aware that it's there might make them more inclined to go and help it. Because they can see it in real time, or they're aware about it in real time. That really can also help make a difference.
Adding on to that, like we tweeted it out to show the world like the plastic in the ocean. So people also are more lenient to like recycling and helping the environment in other ways, even if they're not going to pick up the plastic in the ocean.
Yeah.
Okay. Thank you again, Team Raiders. Team Satellite Warriors, you're on deck. But now let's welcome Team Satickens.
Welcome to our CubeSat Challenge final presentation. We're the Satickens from Taft Charter High School, Woodland Hills. And my name is Soyeon.
My name is Hyun Woo.
My name is Logan.
My name is Jaden.
My name is Akash.
Our Satickens project statement is that we understand that the collection of plastic waste in the Earth's ocean is an ongoing challenge for the global community. To monitor the accumulation of plastics and ultimately remove them, the Satickens have developed a satellite solution. Our solution is to develop and assemble the CubeSat subsystems to power and support an optical payload. The CubeSat in LEO polar orbit will take surface photographs of the Earth's oceans, rivers, and lakes. It will then wirelessly transmit the data to our receiving ground station. Once received at our ground station, our team will analyze the data to detect plastic and determine its position and contents.
We started by designing our CubeSat, which we made a model in Autodesk to organize the components and make our successful build for the mission. We also included an electrical wiring diagram to show the connection between the Raspberry Pi and the IMU. And now Jaden's going to talk about the system overview.
Okay, so to better show our CubeSat system, we took our system block diagram from our design review and we updated it to be more specific, especially in the ADCS subsection. We separated our IMU into 3 different parts. And we also added more data and power lines to be more like specific and make sure it's more accurate. So this should show our overall CubeSat.
This is an overview of the CubeSat software, where we've set it up in terms of the states of the CubeSat. Starting off from the imaging state, we have a few conditions that need to be met for the CubeSat to take a picture. We have a time interval of 10 seconds, so we don't have repeat pictures, and we ensure that the CubeSat has a flat angle, so the angle is pointing towards, the pictures are pointing towards the Earth. And finally, the satellite has to be above water and not above land. When these conditions are met, the camera system will take a picture, and then the whole CubeSat will transition to the standby state. But before it does that, it downlinks the data to the GitHub, the GitHub database on the ground. From the GitHub database on the ground, we can move to the ground station, which is our high school. We can pull all of those images from the Git repository and run our image processing algorithm. Our image processing algorithm reads the image, then it converts it to HSV. Then we blur the image because due to our extensive testing, we realized that when there's a sharp transition between colors, there's artifacts in the image detection, and it's easier to detect the plastics if we blur it. Then we apply a certain threshold of hue and saturation values to pick out where the plastics in the HSV image are, and using a box filter position map, we're able to find the position of those black and white segments on the picture. And if we apply that box filter map to the original RGB image, we're able to detect the position. Using a similar threshold of values, we are able to also isolate the RGB image's plastics as seen on the image on the right. To apply this algorithm, we took 3 images, as we can see on the left, and this was conducted during the tech demo. These images had bad lighting conditions with shadows over the plastics, but we were still able to run the algorithm on them. Running the steps that we've previously mentioned, we get the images on the right, which isolate the plastics in the image.
We were able to obtain these results using our test demo environment, which was used to simulate the CubeSat in a fixed LEO orbit. To create this orbit, we constructed a robot that was autonomous and can run through the track that had a gantry arm to suspend over the water, which would hold the CubeSat at a set height throughout the test. In the experiment, we used white poster boards that represented the water and black table that represented the land, which the camera only took a picture when it was over the water, which was the white poster boards.
There are some smart requirements that our CubeSat has to meet during its mission. So some of the key points here are that it should take images and detect plastic in the ocean. It should operate for 5 years about and communicate with the ground station live time. It should also operate in the low Earth orbit and switch from standby to camera states when it's over water and in sunlight.
For the purpose of setting our CubeSat into space, our test simulation environment will transition into the flight system environment. It involves the CubeSat orbiting in the LEO polar orbit, and it is 800 kilometers above the Earth's surface. The autonomously driven bot shown in our demo will not be moving the CubeSat. Instead, it will be launched through a rocket and deployed into orbit in space. The CubeSat shall not take only 3 photos, but will take multiple shots during the time the CubeSat is orbiting when the sun is shining, which is approximately 45 minutes. The standby state and the transmitting data action will stay the same. However, the standby state duration will be longer for about 45 minutes, and the CubeSat will require to transmit a larger file of data to our ground station. And finally, at our ground station, we will analyze the data for plastics on the surface of the bodies of waters using image processing.
For our future mission, we can make some improvements to our CubeSat, and that includes increasing the battery life to meet our power requirements. We can also take images continuously rather than just taking 3 photos as we did in our tech video. And finally, we can improve our image processing software for better detection of plastic.
While we were working on this project, we had a couple major setbacks, which we were able to mostly overcome. These setbacks fall into 3 different categories: programming, building, and testing. In terms of programming, we had some issues with our CubeSat downlinking its photos to our GitHub because I believe the version differences between the 2 different repositories weren't they were wrong. So we had to sometimes delete our code on our CubeSat and reclone the repository for it to work. In terms of building, some of our CubeSat parts wouldn't fit together, especially the corner rails on our CubeSat. So we just had to drill new holes in to fit. And also the solar panel provided didn't have enough power. It didn't have enough power output to sufficiently charge our CubeSat while it was operating. So every now and then we would have to disassemble the CubeSat and then charge it, and then we put it back together again. When we were testing our CubeSat, our timing was a little off, as you might have saw in our tech demo results. Our 3rd image was a little bit off. And also we didn't really have enough time to develop a system which would ideally continuously photograph the ocean and then see if there's plastics and then delete the image if there isn't.
During this project, we learned some lessons. The first was creating and dividing work each day, allowing us to reach our goals through the use of Gantt charts. Secondly, we never ever delete any code immediately without considering what might be the cause of the downfall of the program. Thirdly, when you are stuck, have multiple people beside you, yourselves, try to solve the problem and then compare or combine your solutions to create an overall better solution to our problem. Finally, always plan for something to take more time than you think it will. More often than not, something will go wrong.
We'd like to say our thanks to our mentor, Mr. Goldstein, and our coach, Mr. Shining. And if there are any questions, feel free to ask. Thank you.
Thank you, Team Satickens, and congratulations on completing the Build a CubeSat challenge. Now open it up again for questions from our judges. We'll start with Patrick.
This is Patrick. What is the trade-off between processing the image in the satellite versus processing it in the ground station?
The thing with the image processing is that the algorithm that we run, it will take a lot of power. Power budget already is an issue when we're continuously taking images in space, especially with the bad solar panel. So if we're processing them on the ground station, it makes it easier. But the trade-off is that sometimes when you downlink data, you might lose some of that data, or it might be lower in quality. So we might not get clearer images than we might have gotten on the CubeSat.
Now I think you have another question from our judge Hero.
Hi guys, great job. I have two questions. So very impressive, your robots. Did you make this as a part of your project along with the CubeSat? And the second question is, you use a white background as a test for your imaging. Does your program work if you use a different background or possibly with a background with a pattern that's similar to ocean waves?
So we made this robot along with the CubeSat to be able to simulate it accurately in an LEO orbit. This just helped to make the image taking process less shaky and more precise. So we found that helped.
And for the white background, what we wanted to represent the image processing in a better light to make it clearer for the viewer. It's just a matter of adjusting the thresholds of the RGB and the HC values to filter out the blue color.
Okay, great, thank you.
Great, thank you, Team Satickens. Team GonkBots, you're on deck, but now let's please welcome Team Satellite Warriors.
Okay, sorry. Okay. Good afternoon. I'm Jamie Sims. This is Darryl Lubin, James Overholt, Kaylee Service, Sabrina Boyle, Luke Venable, Charlie Cairns, Connor Jason, and Mallory Chase. Kevin John unfortunately could not make it today. And we are the Satellite Warriors.
Okay, our CubeSat is based off of a 5-state state machine, which controls the actions of the CubeSat. The state the CubeSat is currently in is determined at the moment mostly by the AECS inputs of the attitude and the acceleration of the CubeSat. The 5 states of the CubeSat determine whether the CubeSat is waiting for its next command, taking a photo of the ocean, analyzing recently captured photos, sending text commands and analysis results to the ground station via Bluetooth, or hibernating to charge the CubeSat and preserve its energy. The CubeSat will be orbiting the Earth at around 300 to 400 kilometers above the surface of the Earth. The CubeSat takes photos of the Earth's oceans from this height, and it sends those photos through our image processing code to determine the concentration of plastic in the image. If this surpasses a certain threshold, it will be saved as an image on the CubeSat, and if it is above an even higher threshold, it will be added to a queue of data to send to the ground station.
The results of the image processing code will also be sent to the ground station inside of a text document containing details on the percent of plastic in the image and the location and time at which the image is taken. Hypothetically, every time the CubeSat passes over the ground station receiver, the CubeSat sends a heap of data from the cube down to the ground station. And this takes roughly 1 to 3 minutes to send with Bluetooth to the computer. However, our code is not adapted to detect when it is over the ground station, and the CubeSat simply waits for a certain amount of time before sending the photos to the ground station. The CubeSat will use the images that have been analyzed and the coordinates of those images to send to the team that can specifically locate the plastic and clean it up, with the urgency of the cleaning determined by how much plastic is in the image.
So we performed several tests in addition to our final demo. Here you can see the before and after images of one of our earliest tests from when we first finalized our code to locate and gray out the ocean water, leaving only suspected plastic objects. The first image is a satellite image of a plastic object floating in the ocean that we found through online research. And the second image is that same image after being run through our code. The code, as you can see, worked very effectively, eliminating all of the ocean water and revealing just the plastic object.
To test our CubeSat's functionalities, we decided to suspend it over one of our team members' pools.
We knew that we need to be very careful to avoid our CubeSat falling into the pool, so we secured a string to all four corners of the top panel of our CubeSat, and then we tied a loop to allow the string to hang off the rope above the pool. One end of the rope was fastened to an outside light on the house, and the other was securely wrapped around an umbrella on the opposite side of the pool.
This first image is the picture that was taken by our CubeSat in our final demo. The second image is that same image after being run through our code. It can be seen that at the edges of the second image that some of the water was detected and grayed out as it should have been. Unfortunately, the water we used for testing was too lightly colored compared to ocean water for the code to properly detect and eliminate it. So the final demo was not as successful as previous tests had done with downloaded ocean images. The processing code was not as efficient as we would have liked, taking 17 minutes to run the processing code, analyze the image, and eliminate the water. This is because the code runs through every color for each individual pixel.
When talking about the parts of the CubeSat that have to be modified in order to actually be functional in space, we have to change almost everything except maybe the Raspberry Pi. The camera, solar panels, thermal system, structure, image processing, communication system, and ADCS are all not up to the standard needed for space, and each of these issues on its own could cripple a CubeSat. So most of these elements would need to be replaced.
The camera that is currently in use in our CubeSat already lacks the adequate resolution and zoom to properly be used in the trials of our prototype. An adequate camera with much better zoom and resolution would be necessary for a scaled-up system in flight.
Our current power input is also insufficient. Our solar panel's current is around 0.002 amps. Our solar panel would thus be absolutely useless and not at all able to sustain our CubeSat in flight. For a scaled-up flight, we would need better solar panels and probably more wonderful.
The thermal regulation of the CubeSat that we currently have is very minimal. It only includes the base thermal regulation of the Raspberry Pi. This thermal regulation would not be sufficient for our CubeSat to survive in space. We would need better thermal regulation systems, and we would need insulation to properly keep the CubeSat functional. Additionally, the acrylic casing and aluminum supports that we use in our CubeSat are not sufficient. One of the key aspects of scaling the CubeSat into a flight system is actually getting it off the ground. Our CubeSat in its current structural case could not survive takeoff, landing, or even just orbit. It probably could not even survive a 1-foot fall off of the table.
It currently takes 17 minutes for our software program to analyze the picture. With an orbital period of 1.5 hours, the prototype CubeSat could only take and analyze 5 pictures in the moment. This makes it incredibly inefficient in actually detecting and making a difference in the quantity of plastic in the ocean. The analysis also currently runs on someone's laptop, and most likely runs slower than the Raspberry Pi. This means we need to develop an image processing solution that can run much quicker than our current solution.
The current communication system on the CubeSat is very limited. The time it takes for images to be sent increases largely as distance between is increased. The CubeSat takes more than double the time to send the image from the ground station as moved 100 feet. Our CubeSat relies on the use of a Bluetooth connection between the ground station and the Raspberry Pi, which would obviously not be sufficient to communicate in orbit. A different form of communication would be required.
Currently, we also go very limited to ADCS. We only have an accelerometer, a gyroscope, and a magnet. The first issue is the meager attitude determination system. We have no GPS or star tracker, both of which are regularly used to track position and navigation. However, more importantly, we have no sort of control over the position or attitude of our CubeSat. We have no magnetorquers, reaction meters, or anything else that can control the position or attitude of our CubeSat. This is clearly going to be a big issue if we're going to try to figure this out. We would need to add such hardware modules onto the CubeSat before we send it to space.
Throughout the entire course, there have been many difficulties. From having to go to Koopmans for screws to almost destroying the CubeSat a few times, there was a lot to learn. From this experience, our team learned many valuable lessons on leadership, teamwork, and timeliness. Many members of the team also learned many new things in the realms of both software and hardware, whether it be how to locate IMU inputs or learning the language of Python. When first tackling the problems, we started assigning people to different groups pretty much at random. We pretty quickly found out that it'd be very beneficial to assign people to different sections based on their strengths and interests. This allowed each member to enjoy contributing their part in this CubeSat challenge.
I was in charge of creating a working demo for detecting plastic in the ocean. From working with the team, we had a few different approaches to the problem. those being finding the average RGB values of plastic, or eliminating the water from an image. But we concluded with a program that grades out a range of colors that represent water, and from there we would be left with all of the plastic from the image. Creating this was quite the challenge because there wasn't an easy way to manipulate the pixels in an image. I first had to teach myself how to use the module PIL, hello, and the web colors because they carried functions that would be very useful. The PIL module allowed me to create a new image that stored pixels of plastic and grayed out pixels of the brown and water. The web colors module, however, was not as helpful because it stored a method called RGB to name, which theoretically is supposed to take any RGB value and assign it to a CSS3 color code name. But for some odd reason, it was very prone to failure. From this, I had to generate a function that converted an RGB value to hex, use the CSS3 hex to name library from the web colors module that gave a CSS3 name for every hex value, and loop through the entire dictionary to match a hex code to a CSS3 color name for every individual pixel in the image. From start to finish, I can definitely say that I've learned a thing or two about researching and what I need to solve a problem.
During our main class demo for CubeSat, we learned many things about its functionality and how to improve our procedure in the future. Our test involved suspending our CubeSat over my pool by fixing a rope that can follow up all objects on each side of the pool. This gave a narrow camera angle, which was not really wide enough to fully capture the area we had set out for plastic in the pool. In the future, if we were to do this again, we would consider using a drone or another method to suspend the CubeSat higher to increase its field of view. We had problems with leaves cluttering up in the pool, which impacted the results of our image processing code when we put the images of leaves through. In the future, we would be more careful to clean up the pool beforehand or choose a cleaner pool. We also had some mishaps with the code written by one of our team members, and we had to revise it quickly, yet this did not cause any large problems. Thank you for your time. Do you have any questions?
Thank you,
How would you
Satellite.
differentiate? So how would you differentiate between plastic and other objects in the ocean, like a ship?
Can you repeat that? We can understand. Sorry.
So how would you differentiate the difference of a ship versus plastic that you would see in the ocean?
So that was one of our troubles that we had. We originally were going to choose a machine learning algorithm that we ended up not being able to continue with that would be able to differentiate between ships and plastic. But with Daryl's program, it's definitely hard because the pixels are different.
Yeah, I think with more time on our hands, we have been able to generate a machine learning algorithm that would work coincide with the Python programming. That would have kind of like eliminated those things like boats or ships in the ocean and kind of just singled out like plastic was the one thing that we're looking for in an image. Because what it does, right, is that it eliminates specific things like just water right now. But with the machine learning, you could eliminate other things like ships and boats. So answer your question.
Thanks.
So I just had a quick follow-up question to that. You know, you described in your tech demo how it was difficult. I guess the pool water was a little bit clear, right? So it was hard to differentiate. Can you comment on if the challenge, say, to detect clear plastic, even if the water was darker? So if you had clear plastic bottles flowing in a dark ocean, do you think that would have been detectable?
So what we've implemented also is an edge detection function that does kind of single out different edges that are separate from the water. And with that, it kind of shows that if there is an edge here, that it may also be plastic in the water.
Got
so
it.
That's how we're kind of singling out the clear plastic color.
Very good.
Great, thank you, Satellite Warriors. And congratulations on completing the Build a CubeSat challenge. Team HawkSat, you're on deck, but now let's please welcome Team GonkBots.
Okay, so this is our CubeSat file presentation.
Hi everyone, I'm Charles.
I'm David Sid, and Sid for short.
I'm Alex.
I'm Jonathan.
I'm Christopher.
I'm Isabella.
I'm Shivna.
And the other members on our team are me here, Fred, and Steph. And our team mentor is Dan Strickland.
All right, so into our CubeSat. So the mission was general, to identify colored pieces of plastic in an ocean from a bird's eye view from a tested large height, per se. So our CubeSat accomplishes this in the subsystem overview. So we take pictures using the Raspberry Pi camera, and these pictures are communicated with the ground station through Bluetooth, and the image processing algorithm processes the colored plastics and works so that it reads each pixel and determines if it's plastic or not. And then through that, we can recreate an image with where we find every piece that is plastic in that given image. We also sought to test our CubeSat in a way that was as close to possible as a real CubeSat would be tested. So we used a blue tarp with different heights to almost simulate the waves of the ocean. And through this, we were able to figure out a way for our CubeSat to differentiate between heights and differentiate the waves so that we could figure out the plastics. So this is our CubeSat, this is our CAD design. Our hardware components were broken down through subsystems. So we had hardware, software, electrical, all that. So Raspberry Pi, we used as the computer, and we used the micro SD card, Raspberry Pi camera to take images. We used the IMU and collected data such as acceleration and angular velocity. We had a nice battery that CubeSat provided with us. We had acrylic panels and acrylic side brackets. Obviously, in a real CubeSat, we wouldn't have acrylic panels on our CubeSat, but in this test, it was a very good demonstration of what a real CubeSat would look like. And electrically, we had female-to-female jumper wires. So some key features of our CubeSat were the battery, the Raspberry Pi, and the 1U feature of our CubeSat. So it is a 1U CubeSat. So the key processes of our CubeSat were to recognize colored plastics using imaging and software processing. So as I said before, we'd go pixel through pixel and essentially determine if it's plastic or not, and then transmit those processed images to the ground station. We used a Python tool called Bluetooth Manager, which allowed us to communicate between the CubeSat, the Raspberry Pi specifically, and our ground station. And so the key systems we have, which are the system overview, would be the power system, communications, which is through Bluetooth, software, and hardware.
This is our tech demo video. Yeah, I'm going to speak while this is happening. So I stated in the video, the satellite's camera takes a picture when the IMU detects acceleration of over the threshold of 0.1 units. And we couldn't create a full circular orbit because of the limited supply of tarps we had. So in order to simulate this, we had more plastic to the tarp every time we moved our CubeSat away from the tarp. Next. So these are our final test results. So to give some context, we our tarp was our water, and the objects on top of the tarp were our plastics. So our code detects the plastics, and the plastics detected are colored as black, and the part that's not plastic is white. So we also made the bumps on the tarp we used to simulate waves. So, and our code goes through pixel by pixel and detects if the pixel is within a specified range of blue. And if it is, then we assume it is water. And if it isn't in the color range, then we assume that it is not water and is plastic or trash. So some possible sources of error we had were, well, one noticeable thing we had was that our tarp detected some of the blue as plastic. So it was like very noticeable. Another source was our code was not able to detect the whole shape of some of our objects. For example, the plastic water ball cap we had in the picture on the right. It did not detect the whole shape. And other sources of error were lost data between our CubeSat and ground station and plastics out of visible region of the camera.
So in terms of scaling our CubeSat to be more flight and space applicable, we can use materials such as aluminum or titanium plates in place of the acrylic sides so that the CubeSat itself can survive and face the extremities of space. This is because plastic in our CubeSat would melt in space and render the CubeSat useless. We can also use a more durable and lightweight shell to resist the space forces such as gravity and air pressure. We can also make the hardware airtight by adding layers. This can successfully create a tight space where the CubeSat can work for a long period of time without eroding or breaking down. We can also improve or increase the power supply and solar panel strength to get more solar power. And this is because if we do this, we can function more efficiently in detecting plastic in the ocean. And we can also add an infrared or radar system to our CubeSat, which combined with the camera system can detect plastics much more efficiently and faster. And this is because as of now, the camera system only detects plastic through a color coding system in space. So by adding this infrared or radar system, we can fix many of the problems that we face with just a color coding system, such as detecting plastic that's colored blue. And we can also finally add a more powerful or higher resolution camera system. And this would help us a lot because we would be able to take cleaner pictures at a distance and make the CubeSat much more functionable.
When scaling to a flight spacecraft, we would improve our software for detecting plastics. We could use AI or machine learning models to detect plastics with greater accuracy. Another way is to improve the range of detection by improving camera quality. In our tests, we often found it hard to differentiate between two different plastic objects that are placed next to each other. So an improvement we could make is to have the software outline the plastics to identify them with greater accuracy.
When constructing a machine like the CubeSat that has many different requirements and parts, it is essential to plan both the mechanical and software components prior to building and programming. Just like in the engineering design process, we considered all of the criteria for the solution and did some preliminary research before deciding on a plan together.
It's also important to consider like the satellite links for the CubeSat and how data will be transferred. So we use a variety of equations and other calculations to find out how much data is lost and how the data would be transferred. And this would be important to find like the optimal data transfer time and how often we should transfer this data to the ground station.
All right, so to finish this things off, so the last lesson we learned was about like satellite power. So it is essential to be aware of the satellite's power usage. If the stored power is used at a greater rate than the solar panels can charge it, it will hinder the abilities and efficiency of the satellite. So in order to take care of this issue, it is important to calculate how much power the satellite is using. In our case, the satellite required 2.485 watts of power to run. The solar panel that we received was faulty and failed to produce enough current to keep the satellite running. So the one that we got only gave us 0.6 milliamps. And the one that we were supposed to get should have provided us with enough current to keep the satellite running, which would have been 0.1 amps. So since we had a faulty solar panel, we ended up using the battery as a main source of our power supply, and which provided us with quite a lot of current to keep our satellite running, which was around 2,000 milliamps an hour. And of course, there are many other factors to consider as you're trying to effectively use your power. So such as like the amount of speed, the amount of data and the speed of data being transferred and received through Bluetooth, and how long your code runs are some of the most significant things to consider. Because if your code is running for too long and your data transfer is inefficient, the more power your satellite will require.
Thank you so much for listening to our CubeSat final presentation. I hope you enjoy, and I hope you learned a lot about our CubeSat engineering design process.
So in the test video, you used the accelerometer to gauge taking a picture. You said that you need to register over a certain threshold before taking the picture. What is your reasoning behind that?
Well, in an actual test, we reasoned that whenever, we always reason that a satellite's always gonna be moving whenever it's doing its processes. So we try to always have the acceleration at a certain threshold. So after it reaches that threshold, then it will start taking images, because usually we're not just going to use the CubeSat as a stationary method to detect plastic. There would be much more efficient ways of doing that instead of having an actual satellite be having a stationary role instead of a orbital role.
I see. Thank you.
Hi. On your chart about space hardening your hardware, you mentioned you wanted more airtight hardware. I'm curious why you thought that.
Well, we didn't want to have many different gaps in our hardware, because the more space you have, it lowers the type of things you can do with that satellite. So if we have a much more compact CubeSat, then we would be better suited to do more processes and have faster imaging processing and a much stronger acceleration system, in my opinion. If we were to upgrade the materials and make it more airtight, instead of allowing any planetary things to be inside a CubeSat. I hope that answered your question.
Yeah, thanks.
Thank you, GonkBots. Congratulations on completing the Build a CubeSat challenge. Team Flat Earthers, you're on deck. Now please welcome Team HawkSat.
Hi, we're Team HawkSat, and this is our final presentation.
I'm Pierce.
I'm Olivia.
I'm Jamin.
I'm Logan.
I'm Alexa.
So here are our contents. You can briefly skim through that. Next up, our physical model. You can see the solar panel, the power pack, the IMU, the Noir camera, and the Raspberry Pi all are in there, and they're connected. Due to the mismachining of the aluminum rails, we had to drill some new holes in the plastic acrylic plates, leading to some of them breaking slightly, but we managed to hold it together with a combination of friction and plastic glue without any apparent reduction in physical strength. Next up, our systems level block diagram. You can see our satellite has 6 subsystems: the power, communications, structures, CNDH, science, and ADCS. And our ground station also has a communications subsystem and a CNDH subsystem. Overall, you can see on the satellite, everything is connected to the Raspberry Pi, which is sort of the heart of our CubeSat. So here's our software architecture. You can see the ADCS system involves using magnetometer data to map out an initial function to see where our satellite is going to be, and then checks that against gyroscopic and acceleration data to make sure it's right. We used a Hamming error correction code in order to preserve our communications and our on-satellite memory. And our science system takes a series of photos, overlaps them in order to reduce for data compression purposes, then sends that down to the ground station, where it's remapped, adjusted to remove atmospheric effects, analyzed with several AIs to detect plastic, and then we used a GIS integration to create a dynamic map of the movement of plastic over time. In our link budget, we can use simple geometry and an orbital assumption is a circular orbit to determine how many photos we're taking per orbit. And then accounting for the fact that we're overlapping every 4 photos, we're only sending the data equivalent of 55,200 photos using a conversion rate through compression of 8 kilobytes per photo using PNGs. We're only sending 41,600 kilobytes worth of photo data using the amount of the CubeSat movement. We can use this to calculate the total amount of data, as you can see above. And we can use the parameters of the system to calculate the Shannon limit. And then we can subtract the photo size from that to determine how much of that data we're using. We have 490 kilobytes worth of extra link budget, which should be plenty for us to send any IMU data as well as our function and any possible code corrections.
So since we are sending slightly different data during the initial orbit for calibration, we are just doing a sanity check to make sure that we are not exceeding the link budget here. So we can estimate that each IMU measurement outputs 9 integers, and assuming 32-bit integers, each IMU measurement is 288 bits worth of data. So then we can then calculate the total amount of data per orbit from the IMU based on the frequency of measurement, and then add the data for our calibration photos. This confirms that not only are we still under the limit, but also we have an even bigger margin, which is great in case we need any code corrections that we realize only once the CubeSat is in space. So our power budget, you can see that our battery provides us with the most power. It has a capacity of 37 watt hours based on product specifications that we found on Amazon. And our solar panel, you can pause the video to look at our calculations. And we basically found that our solar panel will provide us with 0.503 watts. And our Raspberry Pi, IMU, and the camera will collectively consume between 3.8 to 5.5 watts. So because these calculations don't account for wire resistance, we have also included a 9% margin for the greatest power consumed by the Raspberry Pi, which amounted to roughly 6 watts. So over here, we did sort of a mathematical modeling thing on Desmos. We basically did a linear function using our battery, our IMU, the Raspberry Pi, and the camera, and also the solar panel. And we calculated that our CubeSat will last roughly 7 hours. We don't really know how this calculation came to be. Perhaps we messed up on some sort of units, but we could not figure it out. And we do apologize for that. So over here, you can take a look at our mass budget. We won't be listing everything out in detail right now, but we can tell you that our total is 1.1325 kilograms, which is our worst case scenario. So the maximum allowable mass for a CubeSat of 1 U size is 1.33 kilograms. So our CubeSat falls under the limit at 1.13 kilograms, and we are good.
We can determine the data budget using the amount of photos calculated for the link budget and a similar estimate for photo size. In order to compress the photo data, we can use the fact that most of the photo regions look at the same area, and we can greatly reduce the space by only marking the differences in each region. Even accounting for reasonable uncertainty in this process, as well as another estimate of the maximum size of our orbital function, and a margin of error for any additional data that needs to be sent up, we get that we have around 6 gigabytes of space to create our initial code in, which should be plenty. Our CubeSat came in under the weight of less than half a kilogram, or under 1.1 pounds, and also only used 4.74 watts. We subjected our CubeSat to a vibration test. We put it on our lovely green machine, which is the filtration system in each classroom at our school, for 5 minutes, and the green machine shakes very rapidly, and our CubeSat showed no visible damage, and electronics continue to function at optimal capacity. We also subjected the CubeSat to vacuum conditions for 10 minutes, and again, our CubeSat showed no visible damage, and the electronics functioned at optimal capacity.
Then we went through a communications test, and we found out that the CubeSat was able to successfully connect to ground station, and the data was sent at approximately our link budget capacity for 10 minutes. Our plastic recognition test was performed 20 feet above water at the Central Park Reservoir, where we observed several pieces of natural plastic waste. Our system was able to successfully detect every piece of plastic, including blue and clear plastic, along with avoiding false positives like a piece of wood or glass. We also then performed a single event upset test next to a smoke detector, a radiation source. The CubeSat was able to operate successfully for an hour without any errors, with the error correcting code successfully correcting a series of introducing errors.
The CubeSat showed no visible damage and electronics continued to function at optimal capacity during our thermal test, where we exposed it to 100 degrees Celsius for 5 minutes and 0 degrees Celsius for 30 minutes. To recap, our CubeSat performed better than the mass, power, link, and data budget expectations, which were all expected to perform better than the required levels, except for the power budget. Our CubeSat successfully passed all tests, including various physical tests and tests to all part of the software. Our CubeSat was able to successfully identify all pieces of plastic in the testing image samples we took in Central Park and attained a 91.3% accuracy when tested on an online testing dataset of plastic. Overall, besides the power limitations, our CubeSat successfully met all the mission parameters. For future plans, our testing did not reveal any flaws except for the power system. In terms of the power system, we would want to expand the number of solar panels in order to cover our whole CubeSat. Our calculations indicated that 12 solar panels would be enough to continually power our CubeSat, or a single 16.3 centimeter by 16.3 centimeter panel. This should be available within our available remaining swap. Other than fixing the power system, we would want to conduct more tests using more advanced testing equipment, as we had to scale back our tests due to time and equipment limitations, obtain new acrylic plates to replace the ones that broke slightly, further train the AIs to improve the system's performance. Thank you for watching.
Thank you.
Thank you.
Thank you, HawkSat. Unfortunately, we don't have any members of the HawkSat team here live today to answer questions, but please join me in congratulating them on completing the Build a CubeSat challenge. Team Space Hunters, you're on deck, but now let's please welcome Team Flat Earthers.
Hello, and welcome to Team Flat Earthers' final demonstration. This team is comprised of Divya, Nishtha, Swati, Ananya, Akhilesh, Jihan, and Helena. I'd like to start off by introducing myself. My name is Ananya.
To accomplish our science mission, we started off by understanding what our goal was. Later, we came up with ideas to how to build a CubeSat. While keeping the requirements in mind, we started off by building the flat set that could take pictures successfully. Later, we developed the software and hardware transforming the flat set into CubeSat. After facing multiple challenges, we now have a successful CubeSat that is able to take pictures above the ocean.
I'd like to start by introducing the final system ConOps. I know that this was reviewed previously in the design review, but I just thought I'd give you guys a quick overview again. So in step 1, CubeSat wakes up on a time schedule, and then the ground station transmits a signal, and it transmits the schedule for the day. In step 2, the CubeSat points the camera at Earth, and it takes images every few seconds, only when it's over the ocean. Then the CubeSat processes and identifies which images contain plastic and which ones don't. It discards the photos that don't have plastic in them, and then it generates a file of time-tagged images with the size of plastic. Finally, the CubeSat turns on Bluetooth and transmits the file back to the ground station. It waits for a file receive acknowledgement from the ground station before it deletes the file. And after that, the CubeSat moves to sleep mode and turns everything off except for the battery and solar panels, and it recharges while it finishes its orbit and comes back to step 1. Over here, we've got the mechanical assembly stages. So we start out over here with the initial flat set. It just has the Raspberry Pi, the IMU, and the camera. And then we add two sidewalls to it, and then we connect the camera to the actual Raspberry Pi and connect the IMU also to the Raspberry Pi. Over here, we install the battery. As you can see, there's a black wire over here that connects the battery to the Raspberry Pi, and it's tough to see, but there's also solar panels right there. One thing for the battery, we had to attach it using Velcro, same with the solar panels, but since the battery was so heavy, it was very unstable and it kind of kept falling off. So we used a rubber band to secure it in place. Finally, over here, we just closed up the sides of the CubeSat, and that's our final CubeSat.
Hi, so I'll be going over the software overview and image processing parts of our CubeSat. So this is our main Python code, and basically the run through is that it will get the IMU values from sensor.quaternion, and if it indicates that it's facing downwards, meaning it's less than a threshold set by us, it will take a photo. It will then resize the image to be smaller so it's more manageable in terms of data and also processing. And then it will process the image using a method from the ImageRec class, which I'll get into in a second. If that method indicates that it's plastic, it will save the image with the timestamp of when taken in the image name so we can identify where it was taken. And if it was not pointing downwards, it would not take the photo in order to save power. So this is the image recognition class. I'm going to start from the main processing image, which is down here in yellow. Essentially, it will first convert the image to hue, saturation, and value using OpenCV2.convertColor. It will then filter the image into black and white using cv2.inRange, and it will take in these low and high HSV values, which are set by us over up here. And essentially, the function, if a pixel is in between these low and high values, it will color that pixel black, and the rest of the pixels will be colored white. So once it's filtered that image, it will calculate the percentage of water using this red percentage of water function up here. And it just counts the number of black pixels, which are marked as water using our HSV values. And it will return that percent as a percent of the total number of pixels. And then finally, it will return a list with a string describing the image, the percentage of water in the filtered image. And a side note is that the string is found using this orange function called findType, and it takes in these water thresholds, which are also set by us. So essentially, these last two numbers are the minimum and maximum plastic percentages of water. So if the image has between 94% water, 99% water, we're going to label that image as plastic because it has its majority water, yet not fully to be completely water. So it will return a string saying plastic. And then finally, here are some examples of the processed images versus the original. So on the left is the processing that's done by cv2.inRange. And you can see how the H, S, and V values we selected mark all the water pixels as black and everywhere else as white. And then on the right is the unprocessed resized photo that was taken by the Raspberry Pi camera. A small note here is that we were not able to do machine learning because we didn't have time to take enough photos to build a library. But as you can see, the rudimentary HSV processing is pretty accurate for plastic and water.
So I'll be talking about the power budget. First, we can assume that for the max charging rate, and we can get this by looking at the solar panel max voltage, which is 5.5, and the max power of 0.6 watts. Using this, we find that the max charging rate is 109 milliamp hours. This is important because our orbital time for the CubeSat is 1 hour for the science mission and 1 hour for the idle mode, meaning that for however much the battery is drained during the science mission, it has 1 hour to get back to full charge. So then we can figure out the power budget with the assumptions that we have a 10,000 milliamp hour battery, and during the idle time, so during stages from 4 to 1, the battery will consume 0.13 milliamp hour per second. So with this, we can find that we have a budget of 108 milliamp hour, 4 stages, 2, 3, and 4, 2, 3, and 4, where we take and save photos. Then with the assumption that it takes 0.21 milliamp hour per second to take and save these photos, we get the fact that we can take 1 photo every 7 seconds.
Hi, I'm Akhilesh and I'm presenting how we tested our CubeSat. First, we placed a 6x8-foot blue tarp on the ground to represent the ocean. Then we placed different colored shoes and other colorful objects on the tarp to represent the plastic in the ocean. After that, we had one of our group members hold the CubeSat at waist height above the tarp, facing the ground. Then we started up the CubeSat and rotated it so that it recognizes that it's looking at the ground. This simulates its rotation around itself as it orbits the Earth. Then our group member moved it around the blue tarp to let it capture and store images of the plastic. It recognized whether it was over the ocean or over the plastic, and then if it was over plastic, it took a picture and then saved it. After we moved it across the whole tarp, we checked the ground station for the images of plastic to see how successful our mission was.
So here was our tech demo, if you recall.
So the CubeSat is orbiting over Earth. As it passes over water, it begins to face downwards. It's not taking photos until it's fully facing downwards and it sees water. It's seeing water. It sees water. It passes over a large piece of plastic and saves that photo. It continues in its orbit. It sees water. It passes over another piece of plastic and saves that photo. Sees water. Sees water, passes over another piece of plastic and saves that photo.
Okay, I think that no project is done without a couple of challenges along the way. So here were ours and how we fixed them. So starting off with hardware, which there's always going to be difficulties with on a hands-on project like this, that meant for us understanding the blueprints that were given to us. And so an example of that was our camera placement in the acrylic well and the aluminum corner rail holes, because you can see in the picture they were not aligned. So we ended up fixing that by drilling our own holes and also fitting the battery and solar panel in. And we managed to do that by looking through the blueprints. So our use of blueprints definitely improved as time progressed. Also, Bluetooth-wise, the radio could be turned on, but the files could not be sent over Bluetooth, and we weren't able to fix this. So instead, we connected the ground station or our laptop over to by Wi-Fi instead. So yeah, these were the challenges we faced and the lessons we learned.
So if we were to actually launch this CubeSat into space, we would first and foremost need better build quality, stronger materials so that the CubeSat could survive in space. We would likely need image recognition based on machine learning so that it would be able to take photos and process them more efficiently and accurately. We could use a GPS for tracking, but this isn't completely necessary. We would definitely need a more color accurate and a high resolution camera with stabilization so that the pictures wouldn't end up blurry or low res, and they would be much easier, and the image processing would be much easier. We would need larger solar panels so that it could sustain itself in space and not run out of battery. We would likely need to attach a motor so that it could control the orientation of the CubeSat in case it wasn't spinning and it wasn't facing down. We could use a larger link budget so that we can communicate with the CubeSat in space if it was in low Earth orbit, and we would need to revise our ConOps based on the updated data and power budgets, and we would need to incorporate the new subsystems. Thank you for watching. We hope you enjoyed our presentation.
Hey, great presentation, you guys. Could I ask, like, what were some of the considerations you used for actually tuning your HSV thresholds, like different lighting or using like dull or vibrant colors for the plastics?
So we did it all manually because we didn't have time for machine learning, which just means we took a lot of photos, and then we had we actually built this little this piece of code that you could move sliders with the HSV and then see how the image, the in-range function would respond to that. So we used that, we took a ton of photos and then toggled the sliders and then repeated it with different types of like plastic-like simulations in order to make sure we got the large variety. Lighting wise, we only took photos over the blue tarp and we didn't move it around. So lighting wise, we did not experiment too much with that. But based on the different types of plastic, I'd say it was fairly accurate.
Thanks. I've done that too with like the sliders and having your image in front of you.
I guess I'll jump in with a question. In your tech demo video, it looked like you were moving the CubeSat continuously as you moved over your targets, and you would call out, water, now it's plastic. So I guess, kind of a question we talked about in earlier presentations, how sensitive was your ability to detect based on how quickly you were moving around, and was that a factor?
We did not experiment with moving it very quickly because that would blur the image, but we have our code set to take the one photo every 1 second. And we, as long as it's the IMU, of course, is pointing downwards. And we just experimented that. Does that answer your question?
Yeah, thank you. Very good.
Thank you, Flat Earthers, and congratulations on completing the Build a CubeSat challenge.
So actually, we didn't.
Team Yellow Dragons, you're on deck. Now, please welcome Team Space Hunters.
Hello everyone, this is Team Space Hunters and I am Nick.
I am Razi.
I'm Samir.
And I'm Dylan.
Today our team is presenting the mission to find plastic in the ocean for the AIAA BWSI CubeSat Challenge 2022. This slide showcases the coaches, mentors, and members of our team. On the bottom right is a picture of the members of our team at Alvern High School. Today's objectives are to overview the final CubeSat system, discuss results from testing and final demo, talk about lessons learned, scale what we've done to a flight spacecraft, and conclude our work. Plastic has caused a huge problem for all sea life. 100 million marine animals die each year from plastic alone. 70% of our debris sinks into the ocean's ecosystem, 15% floats, and 15% lands on our beaches. In response to this, our mission statement is to detect large plastic debris in the ocean to help remove them. The overall plan for how the designing, construction, and launching of a LEO-based 1U CubeSat is as follows. For the construction portion, all subsystems must be budgeted. Subsystems are finalized and the structure is designed using CAD. Then a different team gets involved in construction and implementing the design. Listed here on the bottom is how we divided up the work to accomplish our mission. And now I will pass it off to Razi.
So here's our final CAD design of CubeSat, which we ended up building. And here's a quick high-level overview of mode of operation. So first, during pre-launch, we ran TechBot, which is our health check script, to make sure that all systems were working fine. And then after that, when launched into orbit, the CubeSat will power itself and make sure that it can calibrate the IMU. If that fails, it will run in the time-based mode and image processing takes place. Images are scanned and sent to GitHub from the ground station, which is a local computer. It will pull those images from GitHub and process the image to detect for plastic. I'm going to be running the flight software CubeBot for the given interval and duration. The first run is going to have 45-second interval and 1 minute duration. And I just started it there. On the other screen, I'm going to run the health check script, which is TechBot. It runs for every second, scanning voltage, memory, CPU, and temperature usage in Raspberry Pi. And right here, you can see the IMU acceleration reading, the gyro reading, and the magnetic reading. It also says the start time and the end time. So now the scan has been complete and the changes have been pushed to the Git, which just means that the pictures have been uploaded. It also shows the total time and the number of orbits. So right here, I'm opening the Git file where the pictures have been pushed. So now we can look at the TechBot stats and we can plot it on a graph. So this shows the fluctuations in the stats that was taken, like the CPU fluctuates, the memory, and also the temperature and the voltage. So let's run Combat on a local computer for demo purposes, and this will be pulling images that were uploaded to GitHub. So right here we tested this picture, and we can see that it's mostly black, and dark mode has been detected because the percentage of dark pixels exceeds 90%. So now let's test a picture which has plastic in it. So this picture right here will be testing, this code right here will be testing this picture, and we have set a threshold of 8%. And because that value is exceeded, it has detected plastic. Now let's run our code which filters out just that plastic. So we have ran it, and it has created this image right here. And this was the original image. So here are some pictures of the prototype test setup that we had. And here are the results from the testing. And we also had some sources of error. Like for example, during testing, only 1 to 2 feet of view of flight was used. And also another problem that we faced was that the resolution was fixed and it wasn't able to be changed programmatically through like software. And here's some results from the testing. We plotted the measurements on a graph, and you can see that the memory and the CPU are the ones that mainly fluctuate. And this is because this is during the startup, and also at the end, it's pushing it to GitHub. It's pushing the pictures to GitHub. And here's some image processing, and the picture on the left is the image taken from the CubeBot, which is not processed, and the right is processed. And we can see some minor flaws here where the green plastic and also the blue plastic are counted as the land and water. So when it's filtering for plastic, they're not counted as plastic.
So these are our lessons learned and some problems we had with our CubeSat design. So first of all, we had issues with connecting to the Bluetooth from our Raspberry Pi. And due to time constraints, we just had to scrap using Bluetooth in our project. Another problem that we had was installing OpenCV. And so we had to compromise, and we had to make scripts that individually count the pixels. Another problem we had was that reflections and the changes in lighting in different environments caused the distortions in like the color that was captured in the camera. So these didn't necessarily give accurate results. And we also had fragile panels. So we tried to drill holes in our CubeSat with the paneling, but they were just fragile and we couldn't do it without some minor cracks on the side. We also had our solar panels weren't working as they were intended, and our panels didn't end up charging our battery for the CubeSat. We also used household items like a swing for constant spinning motion, and because we originally tried to use a manual motion with our someone in the middle just turning and spinning the CubeSat, but that just wasn't precise, so we actually used a swing instead. And then finally, we also had performed simulated testing, and we couldn't get the accurate readings for the frequencies of uplink and downlink because we used the SSH over a wireless network. And since they're in the same network, we couldn't get the data for that. And for our future flight CubeSat missions, we would definitely like to spend more time designing our CubeSat, because when we were planning a lot about the CubeSat, and we just couldn't get into the designing phase as soon as we wanted. And we also want to think more and use more of the resources that we were given, especially like those workshop Zoom meetings where we could ask more questions and get more clarity on what we were asked to do. And then we also wanted to keep the main goal of our mission in mind, but we also wanted to think of more backup mechanisms for our CubeSat. So one of them was, since our IMU calibration wasn't as precise as we thought, we used time-based scripts as a fallback. And then finally, we also definitely wanted to test earlier in our phase so we could find the issues earlier. And that's just so that our issues don't snowball into like bigger and worse problems in the future.
So in order to scale up our CubeSat to a flight-ready system, there's some changes in implementations that we would have to make. So first, we want to make sure our IMU calibration is more precise, and we want to make sure that our CubeSat knows where it is and it's being able to accommodate for pointing at the Earth. We also want to make sure our flight software is accounting for images that aren't successfully transmitted or taken. So we want to make sure that if we do have an unsuccessful transmission of an image, that we are able to save that image and on the next pass be able to successfully transmit it back down to the ground station, just in case there's any scenario where an image isn't transmitted properly. We also want to make sure that there is less interference with the atmospheric loss and free space loss between the communication between the satellite and the CubeSat and the ground station. If we were able to test that, then that would be great. We're inside, we're not really able to test that. So if we are outside and we had, far distance, we want to make sure that there is minimal loss, or we can account for that loss in some way. So there's testing that needs to be done. And for image processing, we want to make sure that we're accounting for green and blue plastics. Currently, we cannot, because in the code we say that that's either a landmass for green or blue is for the ocean. So we want to make sure that we are able to detect like green and blue plastics in the ocean. We also want to make sure that our accuracy is a little better in terms of making sure if there's smaller pieces of plastic, we can see those, and really fine tuning the colored vision process. And really, in conclusion, we were able to design a CubeSat and a plan and design some code that would be able to be used on a CubeSat. We met with mentors and teammates. We were able to collaborate and learn a ton of new things. We were able to construct the CubeSat in a CAD. We were able to put everything together and have a fully functioning prototype. And we were able to simulate and test that CubeSat, that fully put together prototype, to make sure that we didn't have any flaws, or see what the flaws were in order to fix those. And in the end, we had tons of fun. There's a lot to be learned, but there was a ton of fun along the way.
Okay, I guess I'll start, Rebecca, with a question. So great job, Space Hunters. In the next to last slide there, when you were talking about scaling to a flight spacecraft, you talked about a couple of points. I think you had flight software, communication, your calibration of your IMU, et cetera. How about in the power system? If you were building this for a flight system, what would be the changes you'd most like to see in terms of the power system to enable some of your other functionality?
So one of the main things was definitely the solar panel, because the solar panel that we received right now was like unable to power a battery. And I saw that some of the other teams also ran into this problem in the Piazza post. And so we definitely need a better solar panel, and also a better battery would be nice too.
Very good, thank you.
If you were given more time, I'm sorry, if you were given more time, which part of the project would you improve?
So one of our main flaws as of right now was we weren't able to detect blue and green plastic. And so as a workaround to that, our team could we could like outline blue plastics, because the color of the blue would be slightly different than the color of the blue in the ocean. And we could use programs to just outline the plastic, and that would help us identify that.
Thanks.
Great. Thank you, Space Hunters, and congratulations on completing the Build a CubeSat challenge. Mammoth Aerospace, you're on deck. Now please welcome Team Yellow Dragons.
So we are the Yellow Dragons. I'm Ethan Stefanos.
I am Benjamin.
And I'm Habez. Yeah. So for a CubeSat mission, obviously we had to detect plastics in the ocean from space. So this involved launching the CubeSat into orbit, and after a certain time interval, taking pictures of the ocean using software to separate the plastic from the ocean in the image, and sending that back to the ground station and to a GitHub database.
Now on to our CubeSat systems. So we divided our systems into two parts, our software component and our hardware component. So for our software component, we have four main parts. We have the image detection system, which basically uses a color detection software using a Python library, and that filters out the background of the surface we're taking out an image, and it basically makes a mask of the image, which you'll see shortly. And we have an attitude determination Python script, which basically uses the magnometer and the accelerometer to determine the attitude. And if we find that the attitude of our CubeSat is at an angle where the picture that it's about to take won't take an accurate picture of the surface that we're trying to look at. We will receive a message, warning message on our computer, which is going to be our ground station, that states that our attitude is it's at a wrong angle. We have to change it. And for our Bluetooth transfer, we have a Python script that decomposes the bits from the CubeSat, and it sends the bits back to our ground station, and it recomposes the bits on a file to the ground station, and then we have the image on our ground station. And from our ground station, we basically save the image to our Git repository that's on our ground station, which is our computer, and that image then gets pushed to our GitHub, which is our pseudo database that we're using right now. And here's a little more deeper look at the software. Here's a software architect that we were originally going to use, but we didn't fully end up developing because we didn't end up combining all the Python scripts, because a lot of errors resulted from that. And we'll look at that more later on. So for our original software architect, we were originally going to pre-orbit, start up the CubeSat, make sure that the connectivity is working, make sure that the components are working, make sure that the sensors are working. And that's basically going to be the IMU paths. Then we're going to do an image scan, which again, we use a time interval to establish when are we going to take the images when we're in orbit for the CubeSat. Then we create a file to save that image from the CubeSat, and we send that back to our database, which is our computer. Then that gets transferred to GitHub. And for our hardware, we have really mainly 3 pieces of hardware that are all within the CubeSat with the acrylic and metal brackets. So we have the Raspberry Pi, which is basically the computer motherboard that processes all the Python codes and it executes the commands. It also compiles everything. We have the IMU, which is basically an attachment to the Raspberry Pi that allows for attitude determination. It usually it has the gyroscope, the accelerometer, the magnetometer, and it also has, I'm pretty sure, a lot of Python libraries that also allow for some additional attitude determination, but we didn't really look into that. There's also the battery, which just applies the battery to the CubeSat. And there's also the solar panel, but like a lot of other teams said, they weren't functional in the CubeSat, so we just removed them. And yeah, that does it for the CubeSat hardware and software.
Okay, so for the testing results, for our project, we were able to build a code that is able to show where the CubeSat is aiming, and then we were able to take a picture, and in the Raspberry Pi, it processed said picture to invert the colors to easily identify colors that are not blue, because the ocean is blue and most of these plastics will not be blue. And then that image is sent to the ground station and automatically sent to GitHub. And sources of error. Blue plastic, of course, will not be detected because of how we process the images. Our Bluetooth script has the potential to corrupt our image, which I don't know if we have not solved that quite yet, but if we had more time, we would work that out. And our attitude determination is lacking in consistency due to the magnetic fields of the general environment of Earth.
So if we were to redesign it to actually work, in space, one of the things we would have to add would be a flight system, a propulsion system, to actually move it around, and a way of reorienting the camera in case it's slightly off by a few degrees that could end up greatly affecting what it's actually capturing. We would also need to then include materials for thermal dissipation with a propulsion system that would generate a lot of heat. And it would also need a much stronger form of communication and Bluetooth being up in space. And along with that, we would need to change not only the hardware, but some of the software aspects, like being able to detect whether whether something that's not blue is plastic or whether it's actually a boat. And that would be done through incorporating machine learning. So it also might need to be a little bit bigger, depending. It would still be within the CubeSat units, but we could also use some more specific hardware for the mission than a Raspberry Pi. which would it could be potentially smaller, freeing up some space in the CubeSat for stuff like a propulsion system.
Okay, so our lessons learned for this one, we really divided this up into 3 sections that were most prevalent within our development process. So for our software development, originally when we started, we focused a lot more on developing the Python scripts as individual methods rather than keeping in mind that we were going to all combine this at the end, which we did knew that we were going to combine it in the end, but I feel like we kind of lost track of that. So when we did go to combine all the Python scripts that we had made, some of them would cause pretty massive errors, like for the Bluetooth transmission one that decomposes the bits of image and sends it back to our computer. The main issue with that is when we combined it in the final Python script, which was for the continuous orbit pattern, because right now we can only do like a singular mission that's not continuous. But basically for that continuous orbit that we were trying to achieve, it wouldn't work mainly because we couldn't differentiate when the bytes were stopping and which bytes belong to what image. So they would corrupt the image and the shading wouldn't really work as originally intended. And as for the environmental component, that was really mainly prevalent for the attitude and termination. So it had to do with looking at our environment, what could potentially cause the magnetic field and disrupt our CubeSat's attitude determination system. So potentially for that, we could have looked more into the gyroscope, but that also has its potential issues. I think it has mainly with the amounts of times it's orbiting. I heard was a main issue with the gyroscope. And for documentation, we did document our process, but I feel like we could have done a better job at documenting a lot more of the minute details, especially for the software aspect, for the more minute aspects of the Python scripts that we were importing from our libraries that kind of started to not work when we made a big continuous Python program. So that does it for our lessons learned. And finally, we would like to give a special thanks out to our team member, James Lafayette Jr. He was not able to attend this meeting, but he greatly helped on a lot of the Python scripts. Our coach sponsor, Dr. Nyland, and our mentor, Mr. Donnelly, and the founder of this organization, MIT BWSI. Now we will be taking any questions that the judges may have or anything of that regard.
So out of the project, which part of it do you think you have the greatest accomplishment?
Could you repeat that question?
So for the entire project, between software, hardware, and then planning, documentation, which part of it do you think you have the greatest accomplishment?
I would say the software aspect. A lot of our software, as individual parts, our software works perfectly fine. It's just a combination of all those Python scripts into one program that will allow us CubeSat to run in continuous orbit that had main issues. So like our plastic detection system works fine. The GitHub repository to push it and pull images, that also works fine. And also the Bluetooth decompetition works also fine. But it's mainly the combination of that into a big program that's causing problems.
Thank you.
Thank you, Team Yellow Dragons, and congratulations on completing the Build a CubeSat challenge.
Thank you.
Thank you.
Thank you.
Now we'll hear from our final team of the day, Mammoth Aerospace.
Hello, my name is Francis James Adeliga, and this is Mammoth Aerospace's final presentation. Next slide. For our final system overview, our hardware in the CubeSat is the Raspberry Pi as a computing unit. This is powered by a power bank attached to the solar panel, though the solar panel wasn't that useful. We had our Pi camera, our IMU, and the cube acrylic casing, and we also had our ground station for SSH. Next slide. For our software, in our CubeSat, we had a Python script which takes pictures with the camera and downloads them. On the ground station, we used SSH connection to the CubeSat to transfer files, and we had a Python script using OpenCV to detect colors. Next slide. Here is our tech demo video. If you could play that, please.
Hello, and welcome to Mammoth Aerospace's tech demo. In this tech demo, we will demonstrate the CubeSat taking photos and how we will use OpenCV to detect plastic in those photos. We can see that the Raspberry Pi here is powered on, and it is ready to go. Our first step in this tech demo is to make the Raspberry Pi take pictures. As you can see here, I have a red cup, which is going to be the plastic in our demo. So over here in PuTTY, I will make the Raspberry Pi take a photo by running python 3 camera.py. See, it's displaying a preview here, and so we will lift up the CubeSat over this red cup. And over here, you can see that it has taken these 3 photos. The second step of this tech demo is to transfer the files from the Raspberry Pi over to a home computer. In order to do that, I'm using WinSCP. On the left over here is my computer, and on the right here is the CubeSat. Transferring files is super easy. All I have to do is just click this and then drag it over to my computer. Just hit OK, and then I'll drag over all my images. Third and final step in this tech demo is to detect the plastic itself. In order to do this, we used OpenCV. What this program you see here does is detect colors within a certain range and block out everything else that isn't that color. We created track bars so that you can edit like which hues and which saturations it blocks out. So that's this section over here, and then this section creates like a mask based on track bar values, which is what blocks out the colors, and then it combines it with the original image. And then this piece of code displays both the original and result images. So if we run this program, you can see that we have the track bars over here. Here is the original image, and here is our result. As you can see, this program only showed the red color, which was the color of our plastic.
Next slide, please.
Hello, and
so now for our results. As you saw in the tech demo, we used OpenCV to detect plastic, though it was actually just red colors. And this means that we can successfully accomplish our mission, as this could be used to detect plastics. Next slide. Some sources of error or OpenCV and detection limitations. The current program only detects red, and some results may vary from image to image because of lighting. Another issue was hardware failures. Things like the Raspberry Pi camera may not work properly sometimes. And we also had some programming problems. Minor things like just wrong syntax or like bad programming may cause the code to fail or not run properly. Next slide. Onto scaling to a flight spacecraft. Next. Now we're going to watch Sky talk about structure and how it could be scaled to space.
Hi, I'm Sky Kuntaunit. I was the one responsible for building the CubeSat itself, at least the structure. From building it, I can easily conclude the CubeSat itself is not structurally sound of space. The acrylic would never survive the harsh temperatures. Whether it be heat or cold, either way, it wouldn't survive. And the steel screws would also face the same problem. When faced with extreme heat from the sun, the screws would probably melt or expand, which would end up cracking the acrylic. And then when it's cold, the steel could become brittle, same thing as the Raspberry Pi and IMU, which would cause it to fail. The materials that are used to build up the Raspberry Pi would never survive temperatures of -270 C, and we have no thermal systems to counteract that. So in the end, the CubeSat would end up being destroyed. That's it for me. See ya. Hi.
Now we will watch Alexa go over the theoretical structure of the CubeSat.
Hi everyone, I'm Alexa Hadley. For the theoretical structure of the CubeSat, we would use aluminum frames and walls. The aluminum is cheaper, lighter, and it could survive the temperatures of space. To hold the walls and frames together, we would use titanium. While titanium is more expensive, it is stronger and would better hold and survive space. Hold the CubeSat together and survive in space. To hold the electronics together, as well as provide insulation, we would use Kapton tape. The Kapton tape is more expensive than other tapes like Mylar, but it is stronger and would better serve its purpose.
Next
Hi
slide.
everyone.
And, this is Vivian on power.
Power is one of the most important subsystems of the CubeSat because it's what allows the CubeSat to actually work and do what it was meant to do. The source of power is the solar panel, which converts energy from the sun, and this is connected to the battery, which serves as a power/energy storage. The battery cannot recharge itself, which is why we need a solar panel, and together they power the other parts of the CubeSat, including the Raspberry Pi, the IMU, and the Pi camera. Scaling this prototype to a flight system, everything would be on a much larger scale, including the different things we need to take into consideration, including power regulation, which monitors the intake power and regulates output power. This would be needed in cases, for example, when the CubeSat has a very high voltage, but we need to regulate it into a lower voltage. We would also need a thermal system. There's no active way to cool a CubeSat, but we might need a heater which allows the cells to be charged when they get too cold. Again, in an actual flight system, everything would be on a much larger scale, including the power intake and all of the different factors we need to take into account.
Now we will watch Aaron go over thermal systems.
In satellites, the thermal system manages heat to make sure that some parts don't overheat or get too cool, because some parts operate better at different temperatures and malfunction at certain temperatures and can no longer function, which could be very detrimental to a satellite's function. There are several ways to manage a thermal system, such as reflective coating and insulation, which is passive ways of managing heat, and there's also stuff like radiators and thermostats. But CubeSats face the challenge of having a limited power, surface area, volume, and thermal mass, which means that a thermal system in the CubeSat has to be very precise and has to be considered very thoroughly, because it is very difficult to manage a satellite with these limitations. Our cube satellite, and in this case, does not have any way of managing heat and does not have any elements of a thermal system. And as such, it has no way to help sense if different parts are overheating, and has no way to regulate if a part is too hot or too cold.
Here we have Levi on ADCS.
So the Attitude Determination and Control System, or ADCS for short, it's not absolutely essential for this project. However, in space, it would be incredibly essential to a real-world situation. It would be needed for many things, such as pointing the camera down to Earth to take a picture of plastics in the ocean, or for downlinking the data to the ground tower so that it's not shooting a beam of data into space. Now, the system is mostly comprised mainly of an internal measurement unit, or IMU, that was included in our CubeSat kit. The one included in the CubeSat kit, with the proper coding, it can be functional in a real-world mission.
Here we have Communication Systems by Isaiah.
Okay, so this is the communication system of our CubeSat.
Sadly, not much of the communication system is in our final CubeSat, including the link budget, which is missing. The purpose of the communication system is to establish a link between a satellite and ground station. This is done through the amplification of information carried by radio waves, which is received by the CubeSat and processed. Real satellite communication includes services such as telecommunications, data communications, and broadcasting. That would include pictures taken, location of the satellite, and the state of the satellite, as in how well it's doing or if all of its systems are up to date. The link budget is an account for power capability, transmission, and reception between satellite and ground station. And the ability of the communication system depends on the link budget.
Moving on to some lessons we learned. Next slide. What we learned is that communication is very important. We have to inform teammates and keep everybody up to date about our plans, as it helps make the process easier for everybody. We should also plan ahead. It helps us stay organized, and if we know what to do, then it could speed up work. Another thing is to prioritize time on things that are more important. For example, software is 80% of the work, so we shouldn't have spent so much time on the hardware. That's all. Thanks for giving us this opportunity.
So I guess I'll jump in with a question. So in your discussion of your testing for your tech demo, you were focusing on the red cup, I believe. And I was wondering if you could just comment a little bit on how you would address looking for clear plastics, bottles or whatever, floating over a blue ocean. How would that change your approach?
If we were detecting clear plastic, we might use an edge detection program instead of just relying purely on color.
I'd like to ask a question. What was your favorite part of the project?
I'd say my favorite part of the project was just coding the OpenCV. It's just like, I don't know why, but I just enjoyed it and it felt really fun. Like experimenting with all the track bars and colors and stuff.
Great. Thank you, Mammoth Aerospace, and congratulations on completing the Build a CubeSat challenge. Thank you again also to all of the teams who presented today and participated in the very first AIAA BWSI Build a CubeSat challenge. The judges will now have a very difficult deliberation. But before we get to awards, I'd like to share some more of the incredible work that all of you have accomplished during this challenge. Please enjoy this highlight reel from your tech demo videos of your CubeSat prototypes performing their mission.
Hello, welcome to the Satickens tech demo video. My name is Akash Lalman.
My name is Samuel Wei. My name is Jun Sa.
My name is Logan Weinstein.
My name is Soon Kim, and this is our coach, Mr. Shiny.
Hi there.
Our mission is to develop and launch a CubeSat in the polar orbit to monitor the removal of plastic in the ocean. Our CubeSat will detect and take images of plastic on the surface of the water, and will transmit the locational data and the images taken to the ground station to be analyzed.
Welcome to our demonstration test. And our design is to simulate the CubeSat to orbit around the polar orbital. And the contents of it is the satellite, the autonomously moving bot, which will be further described by Logan, and the ground station, which is the laptop, and the hotspot, which is from the phone. And on the test bed, you can see 3 whiteboards, and those 3 whiteboards are representing the ocean. And on top of it are the plastics.
We decided to autonomously simulate our mission because we would get a much clearer result from the picture that we take when it's steady, as opposed to walking along the route with a shaky camera. So the main part of this autonomous robot is the arm that it has, And what the arm is meant to do is to suspend it out so that it takes a clear picture of the plastics, and it allows for the picture to be taken without the robot in the view, and it encompasses the whole poster board in the picture. So all we have to do to start the robot is press this button on the side, and once it reaches the end of the track, it senses that it's in standby mode. So what we have to do is stop the robot with this switch on the side.
Hello, my name is Mallory Chase, and we are the Satellite Warriors.
Hi, my name is Sabrina Boyle.
My name is Charlie Cairns.
Hi, my name is Kevin John.
Hi, my name is James Overholt.
Hi, my name is Connor Jason.
Hi, my name is Darluvin.
Hi, my name is Kaylee Service.
Hi, my name is Luke Venable.
Hi everyone, my name is Jamie Sims.
To test our CubeSat's functionalities, we decided to suspend it over one of our team members' pools. We knew that we needed to be very careful to avoid our CubeSat falling into the pool, so we secured a string to the top panel of our CubeSat. We then tied a loop to allow the string to hang off of the rope above the pool. One end of the rope was fastened to an outside light on the house, and the other was securely wrapped around an umbrella on the opposite side of the pool.
Just a reminder, the solar panels we were given were not able to generate enough power because the current running through the solar panel was incredibly small. Therefore, we have decided to exclude it from our final demo testing video.
The moment the CubeSat is plugged in, the flight software is initialized and the CubeSat is put into the idle state. I programmed a state machine which switches between the 5 different states that the CubeSat can be in. These states are idle, photo state, analysis state, communication state, and hibernate. When turned on, the satellite will wait for a minute before switching automatically to photo state to take a photo. A photo will only be taken in photo state if the CubeSat is facing towards the force of gravity and its acceleration vector is low enough to avoid blurry photos. Once a photo is taken, the CubeSat transitions into the analysis state. Analysis state currently does not have photo analysis fully implemented into the Raspberry Pi state machine because it takes up too much time and processing power, and the Raspberry Pi would be put onto standby as our current image processing code takes about 17 minutes to run. After the image is processed by our code, the state machine will determine whether or not the image is worth being sent down to the ground station. This will be determined by calculating the percentage of the photo which contains plastic and testing whether said percentage passes a certain threshold, and then deciding based on that test what to do with the image, whether to discard, save, or send.
Hi, I'm Logan Reich. Welcome to Team HawkSat. This is our testing presentation.
I'm Olivia. I'm Pierce.
I'm Alexa.
So first, our physical model. As you can see, we have all of the parts on here, including the aluminum side rails, various smaller aluminum side brackets to hold it in, all of the acrylic panels, the battery pack, the Raspberry Pi, the camera, the IMU, and the solar panel. The battery pack is hooked up to the solar panel and the Raspberry Pi. The Raspberry Pi is also hooked up to the camera and the IMU as well. Some interesting things to note about our physical model will be covered on our next slide with the modifications. So first, our first modification was we had planned in our software overview in our last video to have a power checking system, which was removed due to technical constraints regarding the OS system on the Raspberry Pi. We had a couple changes in our physical model plan, namely the addition of Velcro to hold on a couple parts, mainly the battery pack, and an additional L-brace and standoff to hold the solar panel in place to prevent it from moving around outside of it because of the wires. Additional holes had to be drilled in the acrylic panels to overcome issues in the side rail machining. During that drilling, a couple of the acrylic panels broke, but all of the snap parts are held in place with friction, repaired with plastic glue, and make it totally structurally fine, as you will see in the next couple of slides.
So after performing a couple of measurements, we found that our CubeSat came in under the weight at less than half a kilogram or under 1.1 pound, and also under the expected power as it only used 4.74 watts. We also decided to do a vibration test by placing our CubeSat on top of a filter. At our school, we affectionately call these the green monsters as they make a lot of noise and they also vibrate pretty loudly. So after we placed our CubeSat on top of our filter for like 5 minutes, we found that it showed no visible damage and also our electronics continued to function at optimal capacity.
Hi, my name's Jaime.
Hi, my name's Ryan.
Hi, my name's Ali.
Hi, my name's Gonzalo.
Hi, I'm Maddie.
This is our technical demo video for our CubeSat. As you can see, we face a lot of obstacles as it's taped around. The holes in the panels were too small for the screws, and the L brackets did not align with the panels. We also had tried to drill it, and we had a lot of trouble with that. As you can see, it snapped there.
Yep. So then pretty much after when we couldn't put in the screws, I just looked at the instructions and tried to put everything into place, and then I was able to fit some screws in to keep it aligned until I started putting the tape around. I took the screws back out, and then I tried to pretty much make the same shape as the instructions showed us so that we could fit in the Raspberry Pi.
Because it was too fragile, we had to add some tape. And the Raspberry Pi, we could just drill it in and it would fit perfectly along with the power bank and the solar panel.
Yep. So this here is the Velcro. It's going to be used to keep everything in place, like the Raspberry Pi, all the cords, the solar panel, and the power bank. But right now, not everything is in place because this is just a technical demo video, and it's not needed for what we're about to show you. Alright, so here we have our Raspberry Pi flat sat build. And here is our monitor, and this is our ground station right here. So here we see the environment we set up for our Python. And right now we're gonna run the Python bottle detection code, as we see right here. This is the detection code that will show how our program is gonna take a photo when plastic is detected.
Hello everyone, this is Team Space Hunters doing our technical demonstration of the CubeSat challenge. Our mission statement today is to detect large plastic debris from the ocean. These are our crew members. From left to right, it is Razi, myself, Samir, and Dylan, and we all go to Alvern High School in Hudson, New Hampshire. Today's mission is to first demonstrate the functions of CubeSat from pre-launch till detecting large plastics. I will be discussing this part. Another one is to demonstrate ground station operations, which Samir will be discussing, and to demonstrate with simulated tests detection of large plastics using recycled plastic material at home, which Dylan and Razi will be discussing. For the pre-launch test CubeSat, we first must make sure the CubeSat is functioning as designed and ready to be launched. And then we will run the pre-launch test, which includes multiple manual and automatic tests. First, we'll make sure the CubeSat built is within the mass budget limit of 3 pounds. Next, we will system powers up and the LED light lights up, indicating the Pi is ready to perform its task. Next, confirming the battery is fully charged and solar panel is functional. Then confirming that storage space has been fully made available and remove any unwanted test data. Then confirming system is up by taking and sending a picture from CubeSat Pi camera to ground station. Finally, if ground station successfully received the photo, check the quality, size of image, and then go to edit.
So the CubeSat is orbiting over Earth. As it passes over water, it begins to face downwards. It's not taking photos until it's fully facing downwards and it sees water. It's seeing water. It sees water. It passed over a large piece of plastic and saves that photo. It continues in its orbit. It sees water. It passes over another piece of plastic. It saves that photo. Sees water. Sees water. Passes over another piece of plastic and saves that photo.
So this is our test demonstration for Mammoth Aerospace with Yudhishthir Kumar, Zubin Carvalho, Isaiah Suso, Francis James Adeliga, Alexa Hadley, Vivian Xiao, Sky Koltanowicz, Franco Duval, Levi Shane, and Aaron Ma. Sadly, due to a variety of different COVID quarantines, procedures, so on and so forth, the CubeSat has not been in a position for the last few weeks where all of us simultaneously have been able to test it and demonstrate it. So instead, during this test demonstration, we're going to go through a walkthrough of what our plan is to demonstrate it. All the software and the hardware has been coded already, but the live demo will probably have our actual demonstrations, so on and so forth. So the CubeSat design follows the schematics that were provided. The Raspberry Pi is hosted on 4 plastic mounts attached to the bottom of a plastic mounting case. GPIO pins 1 through 4 are connected to the IMU, which measures acceleration, stability, so on and so forth. The no-IR camera V2 is connected via its own special connector to the Raspberry Pi as well. It's connected via a USB-C to USB cable into the power bank, and the power bank is charged via connection to a solar panel. And of course, there's 4 sides of plastic paneling all around. The camera itself points down and is housed in a plastic casing. Our software architecture is basically such that we have a program hosted locally on the Raspberry Pi called camera.py. It takes pictures with the camera itself. We control the camera via SSH from the ground station. So whenever we want to take a picture with the camera, we simply run the Python script to take a picture with that camera, manually transfer the file over from the Raspberry Pi to the ground station, and then we analyze it with OpenCV. Our scripts for analyzing images at this point consists of basically analyzing different kinds of color contrast. So in this specific example, we are looking at a red cup on a white background. And what we do is we take this image, we port it over into OpenCV, we mask it, add a bunch of different traffic guards to basically isolate the color we're trying to find, such as red. When we test stuff against a blue background, we try to identify colors. We don't try to identify colors so much when we're looking at plastic bottles. We try to identify different levels of saturation, so on and so forth. And what we're looking for is if the color maps are able to basically discern or look like they are concentric to an object, like it's a closed object and not just some weird thing floating in space.
All right, I hope you all enjoyed that highlight reel. Now I'd like to introduce one of our challenge organizers and judges again, Dr. Hiro Endo, to present awards.
Thank you, Rebecca. And everyone, congratulations for finishing your challenge. Very impressive work. Now I'd like to present the award. Sorry about my kid speaking. But, so starting off with the best design review goes to HawkSat. Congrats. The next one up, best presentation award goes to Space Hunters. Congratulations. And next one, best algorithm design goes to Raiders. Congratulations. This is for the use of TensorFlow, yeah, and algorithm. Okay. Second place and runner up to the best overall work goes to Satellite Warriors. Okay, now with the drum beat, the winner of the CubeSat Challenge, the best overall winner work goes to Satickens. Big congratulations. Congratulations everyone for completing the CubeSat challenge. I'm pretty sure it was a difficult task. And congratulations, Satickens, for being a champion.
Congratulations to all of the teams who participated this year in the AIAA BWSI Build a CubeSat Challenge. You should all be extremely proud of the work you accomplished and how much you learned over these past few months. I'd like to thank all of the instructors who helped put together this course, the mentors, organizers, and judges who volunteered their time for this challenge, our sponsors who made this possible, and all of the coaches and parents who supported their students. Now I'd like to introduce our Beaver Works director, Bob Shin, for a final farewell.
Congratulations. You are all cool-looking Beaver ballers today. Stay safe and stay in touch.